Hello and welcome to Talking Papers, the podcast that we talk about papers and let the papers do the talking. And today we're going to talk about the paper Deep Declarative Networks, A New Hope, published in TPAMI. And today I have the author Dylan Campbell with me. Hello, Dylan.
Hello, thank you very much for having me.
Can you introduce yourself?
I'm Dylan. I'm a postdoc at Oxford with the Visual Geometry group. But when I was working on this paper, I was at the Australian National University working with Steve Gould in the Australian Centre for Robotic Vision.
Another author on the paper is someone that some of the listeners may also know, Richard Hartley. Let's get started. So, for the new listeners, every episode here is structured kind of like a paper. So, we go over the main parts of a paper. So, now let's start with kind of an abstract. So, a TLDR. So, in 2-3 sentences, tell us what is this paper about?
So the paper is about inserting potentially non-convex and constrained optimization problems into your network to inject domain-specific knowledge and improve data efficiency while still training end-to-end. So I guess you can think of this as another tool for adding sensible inductive biases to your network. And an inductive bias is something like what a convolutional neural network does for translational invariance. It's something that's built into the network, which makes sense for the particular modality that you're looking at. For convolutional neural networks, that would be images.
What's the name declarative about? Why declarative?
Good question. So declarative comes from the programming languages community. You can have a declarative programming language, and the word essentially means that you specify what you want to happen rather than explicitly what you're going to do each step. And so that's the philosophy that we're taking in this paper, specifying in a network what a layer does by what you want it to do rather than how it does it.
And why is it like a new hope in the title? Actually, it looks like this is only in the preprint. In the final version, there's no A New Hope. So what's the New Hope about?
There is no A New Hope. The New Hope was, well, how do I say it, a Steveism. Steve is the first author, and he really liked it, I assume because of the Star Wars reference, because he thought that this is a new way of looking at neural networks that gives you all of these extra tools to expand what you can do with a neural network and address some of the issues that people were able to do before deep learning. So things like being able to have guarantees, being able to have constraints, being able to have optimization algorithms that you can just substitute in once you get a better algorithm. And these sort of things he wanted to be able to incorporate in a neural network. And this is one method for doing those sort of things. So he was very hopeful at the start, and I think he reflected that in the original title. And I was one of the people who convinced him to be less hopeful and remove hope from the title.
Yeah, I'm still hopeful. So let's move to the next section of the paper, the introduction. What is the problem that this paper is addressing?
So at a high level, there's a trade-off in deep learning between expressivity on one side and data efficiency on the other side. And so you can think of this as the trade-off between having a black box that has infinite expressivity if you have infinite data and infinite capacity, but it doesn't have interpretability. And on the other hand, with a white box, which you don't need any data for, and has good interpretability. So you've got these two things that are on either end. And what this paper was attempting to do was providing a way for you to choose somewhere in the gray region between the two by letting you define differentiable optimization layers in your network. So this means that you can make your network more data efficient and more interpretable, and you can provide guarantees about things like optimality or the nature of the output of that particular layer. So for example, does it lie on a particular manifold? And so these things work side by side with normal neural network layers. And so you can go from the spectrum of a fully learned network, fully black box, to fully white box, and choose places in between depending on your problem. So you can make a good selection of that trade-off. I guess one of the things is that the community has already found many uses for optimization inside networks before this work. So it's not like we're the first to suggest that optimization is useful. But I guess what has happened so far is mostly people have found closed form solutions, which they use inside a network, or they've unrolled iterative optimization steps where that's possible. And so this approach instead provides a more memory and compute efficient alternative to unrolling. And you can also use it in situations where you just can't unroll an optimization algorithm.
So zooming out a little bit, the standard way of using neural networks today is the black box version, right? You got your differentiable layers, convolution, whatever you want, and you got your application, and you just use that black box. You give, I don't know, images as input, and you have your prediction as output. And this is like the black box approach. You don't know anything about what's going on inside, and no interpretability, no guarantees for anything, right? And that's the problem, right? You want to know more. You want to get some of those guarantees, and what this paper is tackling is exactly this problem. How do you enforce some constraints into those imperative nodes? That's the name that you use, imperative.
Yeah, that's right. So like explicit functions is we call imperative nodes by the same analogy as declarative. But yeah, I'd say even that like a fully black box network would be just an enormous MLP with infinite depth. Whereas even going towards something like a convolutional neural network is already making some steps towards adding some inductive biases to the network. And so this is just a tool that you can use to add further inductive biases beyond just the translational invariance of a CNN. So you can think of it in those terms as well. But it's always up to the researcher in how they design their networks as to the design choices they make. And so if a researcher uses a CNN instead of an MLP, that's one design decision, and now we're giving them a suite of tools to allow them to make other decisions to be more data efficient, particularly if you have models of the real world that you know must be true and you don't need to learn them. Situations like we know the geometry of how a camera images the real world, and so we know what those processes are, and there's no real need to learn that particular geometry. So from a technical side, the contribution was deriving the gradient for an optimization problem in its most general form. So when you have nonlinear equality and inequality constraints, which may depend on the inputs or the parameters. And so this lets you consider constrained non-convex optimization problems, which are the sort that frequently occur in computer vision tasks. So this isn't an enormous step from the prior work, which considered sort of convex cases, but is more appropriate for many of the problems that at least I was facing when I was a computer vision PhD student. And so it's nice to have these more general forms so that you can select the option that most suits what your problem is. So if you have a convex problem, certainly use a convex solver. But if you have something that's non-convex, this lets you handle it in the same framework. So I guess that's the main technical contribution. But at a higher level, we were trying to, I guess, express a view that you can think of neural networks as being composed of these processing layers, and we're just saying that these don't have to be explicit functions. You can make them optimization layers and still train them end to end. And so we wanted to collect all of the relevant results from the literature into one framework, so you could understand how they all relate to each other and how you can choose which particular result to use for your problem.
Yeah, so this is one of those papers that it's kind of like a hammer paper, right? You have a hammer, and now you're starting looking for nails where to use that hammer in, and there are a lot of problems in computer vision that you need to solve an optimization problem within the network. Moving on to the related work section. Obviously, don't go over all of the related work, but if you have to mention only one or two papers that were inspirational or very relevant for anyone that's reading the Declarative Networks paper, which reference would that be?
So the work that started this all off was Steve Gould's tech report on differentiating argmin functions, and this is from 2016. And so this is the first work, at least that I'm aware of, that made the observation that you could combine implicit differentiation with the optimality conditions of an optimization problem. and you could use this in the context of deep learning. So these things had been considered before. In fact, obviously, implicit differentiation is a very old concept. It's hundreds of years old, but the idea that you could apply it, that it could be particularly useful within deep learning, I think is what Steve realized in this paper. Since then, we've just been working on fleshing that idea out, making it as general as possible, and building the sort of software library to go alongside that.
Yeah, and the software library, we're going to put a link in the description for all of those software libraries, the link to the paper and everything, so the listeners can access it.
And please do send in any bug reports if you find any.
Now to the approach. Let's dive in, start at the very basic concept. How does it work? How does a deep declarative network work?
So the key idea, I guess, is that you can derive the gradient of the output of an optimization problem by applying the implicit function theorem to the KKT optimality conditions. And so I'll explain what each of these things means. So the implicit function theorem is a way of, well, it shows the existence of a gradient, but it also provides you with a way to compute the gradient of an implicit function. And this is the sort of a function where you have all of the variables appearing in the function and then setting them equal to 0 or some constant. So if you have the equation of a circle, then you have x squared plus y squared minus r squared equals 0. And so the left-hand side is the implicit function. And so these things are quite familiar to us in computer vision and machine learning from ideas such as level sets. Okay, so that's the one side of it, the implicit function theorem. And the other side is the KKT optimality conditions. And these are the conditions which provide the necessary conditions for your optimizer having solved the problem to optimality. And this is in a constrained setting. So is your solution feasible? Does it fulfill the equality constraints? Does it fulfill the inequality constraints? And is it locally optimal? And if it's all of those things, then you meet the KKT optimality conditions. And what we show in the paper is that you can use both of these concepts together to form the gradient of the output of your optimization problem, even when that problem isn't convex. So you can have nonlinear objective functions and nonlinear constraint functions and still compute this gradient, which is a little bit different to how you would normally see these KKT optimality conditions. Because if you've ever done a convex optimization course, you know that KKT optimality conditions form a very large part of that. But the insight here is that in this context, they apply for the non-convex optimization, so long as your objective functions are locally twice differentiable. Because I guess you can think of things as being convex in the local neighborhood. And I guess the key point here is that this means that the optimization layers are compatible with end-to-end learning in a neural network. And this means that you can have optimization problems that have arbitrary but twice differentiable objective functions and arbitrary but twice differentiable equality and inequality constraints within your network and still train end-to-end. So that's the main technical point. But I guess the other things that we do in the method is we show what this looks like geometrically. So we give a geometric interpretation for this, which I find quite useful to try to build an intuition of what's happening visually, because I tend to like understanding mathematics in a visual way. And I think this is quite helpful when you're thinking about designing a network as well. So for example, here, what we show is that essentially the equation that we derive computes a correction to the unconstrained gradient, which essentially means that a small step in the gradient direction will stay on the constraint surface. So if your constraint is to stay on the surface of the sphere, then your small step will always be tangent to the surface. And this is in the infinitesimal step size, it means that you're going to stay on the constraint. And that's what you want from when you're doing gradient descent. You want to stay close to the constraint surface so that you're not going off in directions that are not meaningful to your desired output. The other thing that we were looking at is trying to collect the open questions and the challenges that are still exist in this area. So what things do we not have a good handle on theoretically, and also what things in practice are important for using these layers. So examples of this is things like when you have multiple solutions, so you've got a non-convex optimization problem, or you have a convex optimization problem with a flat region, then what do you do in these cases? Because you've got many valid solutions, you've got a valid gradient for all of those solutions based on the theory. But when you're training a network end to end, it's not just enough that you've got a valid gradient. You also want your network to learn something useful. So we're looking at questions of whether it's particularly useful to use things like global search to find a good local optimum in your optimization problem. And that, at least for the problems that I've looked at, does seem to be quite helpful, because it's, I guess, intuitively finding a bad local optimum isn't really going to help the network learn anything useful. So it's, in many ways, it's probably better to try to find the global optimum or something similar to that if you can.
It kind of ties to the results section. Can you give like a practical example that you used in the paper to show those principles?
So the examples we had in the paper were essentially taking parts of existing networks, so things that are familiar to people in deep learning. So the first one is average pooling, and then looking at it through a declarative network lens and seeing what sort of changes you could make to it using this framework. If you look at average pooling, in the literature, one change that has been made already and has had quite a lot of success is, instead of taking your pooled features as a set, taking it as a sequence. So this was the rank pooling work, which Steve and other co-authors worked on quite significantly, and in fact is why the original results for the tech report in 2016 came about, was from this work. So that's one possibility, but in the paper we look at a different possibility, which is robust pooling. So instead of taking the average of the pooled vectors, instead to take a robust average. And you can think of this as selecting the dominant mode in that window. So you could immediately think, well, why do we just select the dominant mode? We could select multiple modes. We could do some clustering. And in fact, you can think of multi-head attention as doing something similar, selecting multiple dominant modes in a sort of pooling operation. But to go back to the simple case that we were looking at in this paper, which is robust pooling, this is taking the dominant mode, applying a robust function, and getting the robust average of the window.
The first example that you just mentioned, there's a very cool notebook showing how that works, right? That you took a bunch of points, you computed their mean, and then with a bunch of outliers, and you computed the mean, and then you showed how with different robust functions you converge to the correct mean and ignore or reduce the influence of the outliers.
Yeah, that's absolutely right. There's a whole bunch of illustrative Jupyter notebooks available at the website, which run you through the different concepts. A lot of the things in the paper are in the notebooks, and a whole lot of extra material that we developed for the ECCV tutorial. So the second example was taking L2 normalization, which is like a very common operation that you use in neural networks, and writing that as a optimization problem, which is easy to do. And so this is exactly the same as L2 normalization, but immediately what you can see is that you could expand this to other kinds of normalization. So you could, instead of doing L2 normalization, which is equivalent to projecting the feature point to the L2 sphere, you could instead project it to an L1 sphere, an L infinity sphere, or a simplex, or whatever you like, whatever kind of polyhedral shape you like. And so we explored projecting to L1 and L infinity spheres, as well as balls, because we wanted to test both equality constraints and inequality constraints. So balls is when the feature can be inside the ball, and that's fine as well. So it's only when it's outside the ball that it gets projected down to the surface. And these are very simple algorithms to run. So there's very, very efficient ways to project to the L1 sphere, and even more efficient ways to project to the L infinity sphere. So I guess the reason you might want to do this is because it it could be thought of as a regularization, but also sparsification, which is useful for adversarial robustness. And also, there are possibilities that it can improve generalization performance.
You had some more results that you showed on 3D point clouds.
Yes, yeah. So those were the theoretical examples, but we did experiments for them as well, as is usual. For the robust pooling, the experiment we chose was to do point cloud classification when you have corruption by outliers. So it's a bit of a toy experiment, but it was just to see whether these sort of robust pooling operators are useful when you have this sort of noise types. And so the setup of the problem was having some of the point clouds from ModelNet and corrupting them with uniform outliers, and then running the same network with and without the robust pooling operator. So we just used a small ResNet 18 network, which uses max pooling. And then we compared that with average pooling, Huber pooling, and a variety of more robust penalty functions. What we saw trend-wise was that as the fraction of outliers increases, the performance of these models is better for the models with increasingly more higher robustness. For example, the Huber penalty function is less robust than the truncated quadratic penalty function, which completely ignores the outliers. And so the more outliers you have, the better it is to have a more robust penalty function. I guess in terms of comparison to the baseline, it performs far better than if you're just using max pooling, which you can imagine would be very susceptible to outliers, and in fact is.
So without outliers, does it damage the results at all?
Yeah, so it's like a 1% damage, 1 to 2% versus max pooling. I guess there is a trade-off there in terms of robustness and expressivity. I don't know whether that trend would continue when you increase the depth of the network or not. It is interesting having this difference between average pooling and max pooling, and then that being reflected by a kind of brittleness towards outliers. And I think that's quite indicative of a bunch of things in deep learning, that training seems to push things towards the edge of failure to get the best performance.
Let's move to the conclusion future work section. So how do you see the impact of the paper? Are there any interesting papers that followed it?
Impact-wise, I guess writing this paper was the catalyst for us to organize a workshop at CVPR. And this was followed by a tutorial at ECCV. And then another group presented an excellent tutorial at the subsequent Europes, all on these topics and related topics. And so this paper didn't really have to do anything other than provide an impetus to collect like-minded researchers together who were already excited about this topic. And so I hope that by doing this, we managed to extend this excitement to new researchers. And I think that was one of the reasons we wrote the paper in the style that we did, because it's, in a sense, it's archival. It's sort of collecting existing results in a very like coherent and unified form, and it's also written in a fairly pedagogical style, in that we've made it quite clear, like sort of the different steps in it, and also accompanied it with Jupyter Notebook tutorials, because it would be a good reference, well, hopefully is a good reference for students who would want to learn about these tools. And I guess that's the main thing, is to give students and researchers something that they can have in the back of their mind when they're attacking interesting problems, to think whether optimization might be useful to include in their approach. And obviously it's not going to be needful in all circumstances, certainly not in all circumstances, but when it comes up, it's good to have in the back of your mind as a tool in your toolkit in machine learning.
Most students right now, they have a problem like, oh, let's throw a neural network at it and train everything from scratch, where there's probably a good solution using some optimization. And now they can use it inside the network, right? Which before was a problem, right? You were blocked. If you want to do something with optimization, you have to disconnect it from the network. You can't train anything end to end, or maybe you could, but just for specific convex problems. And now you can just plug it in as a declarative layer and use it as is.
It's not appropriate for all situations, and and the approach of getting more data and training a black box is still going to be incredibly important. But I guess in not every, you don't have a lot of data in all situations. And so there are certainly occasions where you want to be more data efficient. And being able to inject this domain-specific knowledge gives you a way to be data efficient.
Now to my favorite section of the podcast. What did reviewer 2 say? Please share some insightful comments that the reviewers had in the review process. Was there anything missing from the paper in the initial version that you ended up adding?
So we had some very thoughtful and detailed reviews, so we were very lucky in that way. Clearly from experts in the field, we appreciate that immensely. I guess the main criticism of the paper was that it overgeneralized the theory without testing this theory to its limits in the experiments. So for example, we don't explore any examples where we are learning the parameters of the constraint functions. We just derive an expression for the gradient in this case, but we don't actually have any examples of that. And that's a totally valid criticism, and it's true, we don't do that. And there remains a whole lot to be explored by us and by the community. I think it's still valuable to provide general results, even if you can't think immediately of a particular use for them. It seems to me to be the sort of thing that could be useful, but yeah, I haven't come up with a particular case where I would want to learn the constraints and the shape of the constraints yet myself, other than I guess in very toy and trivial examples. And I guess the other thing that came up in the reviews, which did provide a useful way into thinking about who was reading the paper, was the implementation considerations. So we had skipped over them a bit in the manuscript because we provided the software library, and obviously you have to put a lot of thought into how you implement things, because obviously PyTorch is written in a way that's very efficient to back-propagate and to do the forward and backward passes. And so when you are fiddling with that, you want to make sure that you're not ruining it and you're not doing something in an inefficient way. And so these details have big impacts on the memory and time efficiency of your network layers. And so if you want this to be, as I said, to be a useful tool for people to use, then it does actually matter what you do in the implementation. And so we included in the revisions of the paper the tricks that we used to do this. So things like the usual vector Jacobian products. So you don't ever form the Jacobians themselves because these things can be enormous. Using parallelized computation, so you never actually split apart the batches. And then there's also some memory speed trade-offs that you have to make sensible decisions about in the software implementation. And I think one of the papers that I looked at to get a sense of how this sort of thing could be usefully included in the paper is Brandon Amos and Zico Coulter's original paper on differentiating QPs, where they do talk about the implementation considerations and emphasize that these things are actually quite important, even though for some people that might seem like an engineering consideration. It's actually kind of the heart of a useful tool, is making sure that it works well.
Brendan was also part of the ECV tutorial organizers and speakers. Okay, so I guess that wraps up the Deep Declarative Networks paper. It is a new hope. I would like to thank you very much, Dylan, for being a guest on our podcast. Yeah, I put all the details below. You can contact Dylan with questions and explore his amazing Jupyter notebooks that he and Steve and the team worked on. Yeah, so thank you very much.
Thank you very much for having me.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.